Welcome everyone. Today we are exploring a pivotal shift in the industrial landscape. The move from AI that simply gives us answers to AI that takes action. We call this Agentic AI. This keynote is designed to help executives, maintenance leaders, and reliability professionals understand how to navigate this transition in industrial maintenance safely and strategically. For our board and executive management, the core message is this. Enterprise value is no longer just about model accuracy. It's about how we engineer authority and accountability into the operating model. We are moving from insights to goal-directed orchestration, and the strategic question we must answer is where AI should act, where humans must decide, and how we govern that entire process. Why is this happening now? We are facing a convergence of technology pressure, where agents are being embedded into enterprise software and the harsh industrial reality that maintenance decisions carry immense stakes. In a planned environment, a wrong action can be far worse than no action at all. Our mandate is to capture this new value without creating disconnected pilots that bypass safety and governance. So, what exactly do we mean by Agentic AI? Think of it as an autonomous, goal-directed system equipped with tools, memory, and constraints. Unlike a traditional chatbot that just answers a question, an agent can plan a workflow, call on specific tools, and monitor outcomes. Crucially, it must know when to escalate when it hits its limits. To manage this, we use the industrial autonomy ladder. We don't just turn on AI. We move from level 1 assistance to level 3 drafting, and eventually to level 4 bounded execution. As a principle, we should keep most decisions at the recommend and draft stages, reserving full autonomy for very specific, low-risk digital actions with high governance. Directors should focus on 6 key areas before scaling: authority, accountability, controls, evidence, cyber risk, and value. We need a board-approved framework that defines exactly who owns the result when an AI-initiated task goes wrong, and what hard stops prevent a digital mistake from becoming a physical plant event. This represents a fundamental strategic shift. The new frontier isn't just detecting that a machine might fail. It's about closing the loop from risk detection to executed action. We must view Agentic AI not as a tool, but as an accountable industrial operating capability. Instead of one giant, generic AI, we envision a portfolio of specialized agents, a team of rivals. You might have a condition agent, a spares agent, and a safety agent all working together. Each has defined access rights and authority, while humans remain at the center of the hub for safety-critical decisions. When prioritizing use cases, we start where value is high but action risk is low. For example, manual research and drafting work orders are great starting points. We avoid autonomous equipment control until we have fully mastered the governance of simpler digital workflows. The goal is targeted authority, not maximum autonomy. Value is created by reducing decision latency, the time it takes to go from seeing a problem to fixing it. By automating the research and drafting burden, we increase planner capacity and convert emergency risks into planned actions earlier, which directly impacts EBITDA and cash flow. However, we must be careful. If implemented poorly, Agentic AI just becomes a faster way to create uncontrolled work. We must avoid agents that bypass safety windows or flood the system with low-value work orders. Uncontrolled action isn't transformation, it's just digital operational risk. To ensure this doesn't happen, we need a robust architecture. We're going to look at how we build a stack that moves from raw sensors to governed actions, ensuring that Agentic AI is built on a foundation of accountability. The industrial agent stack starts with a foundation of trusted data and layers on context, like asset criticality and manuals, before the agent ever reaches the orchestration layer. Most importantly, everything is wrapped in guardrails like role-based access and human approval gates. Agents should never sit directly on raw data. They need context to be safe. In a multi-agent system, the orchestrator is the brain that prevents conflicting actions. It ensures that the safety agent and the spares agent aren't giving contradictory advice, preventing fragmented agents from creating unmanaged risk in the plant. Context is everything in maintenance. A vibration alert on a non-critical pump is a minor task. The same alert on a production bottleneck is a major event. Agents must understand hierarchy, criticality, and operating modes to ensure their actions are appropriate for the specific situation. Risk begins where tool access starts. We categorize access from low risk, read-only, to high governance, execute, access. We must remember that just because a model has the capability to execute a transaction doesn't mean it should be granted the authority to do so without significant controls. In the IT/OT stack, agents primarily live at level 3, interacting with CMMS and historian systems. They may read broadly across the stack, but they should only act through governed systems of record. We must strictly respect the boundary between business workflows and actual physical control systems. Safe autonomy requires engineered boundaries. The most critical design work isn't tweaking the AI model itself. It's defining the policies, authority limits, and escalation paths that keep the operation safe. Human judgment doesn't disappear. It actually moves to higher value decisions. Let the AI handle the tedious work of searching manuals and drafting scopes, while humans focus on final safety approvals, production trade-offs, and ethical accountability. We use a decision rights matrix to determine autonomy based on consequence. If an action has low consequence, we might allow auto-submission. If it's safety critical, the system should strictly escalate to a human. We grant authority based on the impact of the action, not just how confident the AI says it is. Before any AI action is taken, it must pass through 3 gates. Is it technically valid? Does it fit the operational reality of the plant? And does the agent actually have the authority to do it? This safety case must be built before a single agent goes live. Managing AI risk requires a lifecycle approach: govern, map, measure, and manage. We adapt recognized cyber and AI frameworks to the specific world of asset criticality and process safety, ensuring we have a structure in place before we attempt to scale. We must also be aware of failure modes unique to agents, like authority creep, where temporary permissions become permanent, or false confidence, where the AI makes a high confidence recommendation based on missing data. We aren't just looking for wrong answers, we are looking for wrong actions. From a cybersecurity perspective, every agent is a privileged digital worker. They need unique identities, least privilege access, and their own audit logs. We must monitor their tool calls and prompts just as we would monitor a human administrator's activity. Finally, the model lifecycle must be as rigorous as any other operational technology. From design to retirement, we need documented evidence of testing, performance monitoring, and decommissioning decisions to ensure the AI remains safe and effective over time. Now, let's look at the operating model. The real business value is won or lost in the handoff, where the AI's insight becomes a planned, safe, and completed piece of work in the real world. We see this as an alert-to-action value loop. It's an 8-step process, starting with detection and ending with learning. The value isn't in the alert itself. It's in the verification that the defect has been removed and the model has learned from the experience. A work order agent helps turn a technical finding into a disciplined request. It drafts the scope, suggests parts, and notes safety risks. The goal here is quality, ensuring the planner has a solid foundation to work from rather than a vague alert. The planner agent acts as a digital co-pilot, checking for resource availability, materials, and safety permits. It increases capacity and improves job plan quality, helping to reduce the time technicians spend waiting for parts or paperwork. A spares agent is crucial for material readiness. It maps the asset to the bill of materials, checks inventory, and flags long lead times. Predicting a failure is useless if you can't get the right part to the job in time to prevent a breakdown. The safety and permit agent acts as a boundary-checking assistant. It can search procedures and prompt for hazard checklists, but it must never replace human judgment for high-risk work. Its job is to make missing controls visible, not to bypass them. The loop closes with the learning agent. After a job is done, we must capture what was actually found. If we don't feed that information back into our data and strategy, the agentic system can improve, and we miss the chance for continuous reliability gains. Moving to the business case, executives fund outcomes, not technology. We need to translate agentic maintenance into measurable uptime, risk reduction, and cash flow to justify the investment. Our financial logic is simple. Annual value is the sum of avoided downtime, repair costs, and productivity gains minus the program cost. Crucially, we only count value once the action is completed and verified, not just when an alert is generated. In this illustrative multi-site case, we see how benefits across 8 plants can add up to nearly $7 million in annual value. The key for the board is to discount these benefits by adoption rates and validate downtime savings with both operations and finance. To manage this, we use an executive KPI scorecard. We don't just measure AI activity. We measure adoption, execution speed, quality of work, risk exposure, and real financial impact. A good dashboard tells you if the agents are actually trusted and relevant. Success also requires a new workforce model. We need agent owners who are accountable for outcomes and SMEs who validate the AI's logic. Agentic AI succeeds when people know how to supervise and govern it, not just when they know how to use the software. Implementation should follow a practical roadmap. Start narrow, prove the controls work, and then scale by asset class. We must ensure we don't scale autonomy faster than our data quality or governance can support. Over 24 months, we move from selecting use cases to institutionalizing the capability. The first year is about building the foundation and standardizing data, while the second year focuses on replication across sites and embedding AI into our standard budget and audit cycles. In the first 90 days, the goal is proof of control, not full autonomy. We decide on the scope, build the integration, and run a pilot with strict approval gates. We want to capture incidents and learn before we ever consider a full rollout. Before scaling, we use this readiness checklist. Expansion is only permitted when asset hierarchies are solid, human approval gates are configured, and value measurement is agreed upon with finance. We scale when the management system is ready, not just when the technology works. Your vendor strategy should focus on open integration and transparency. Avoid black box autonomy where you can't see the audit trail. The architecture must remain enterprise-owned, even if the technology is provided by a third party. Governance is a top-down and bottom-up effort. The board sets the risk appetite. A steering team approves use cases, and site councils ensure local alignment. Autonomy is a business risk decision, not just an IT decision. We clarify ownership using a RACI matrix. For example, while IT is responsible for access rights, reliability is accountable for work order approval. Knowing who owns the action is just as important as the action itself. Every board needs to define its never events. What should never be delegated to an agent? Safety-critical work and permit approvals should be strictly human only, while low-risk document retrieval can be fully autonomous. When management brings this to the board for approval, the package should include the business case, the cyber risk assessment, and the incident response plan. You're asking the board to approve an operating model, not just a software subscription. Let's look at a real-world scenario, a pump bearing risk. The agent detects the vibration, drafts the work order, and identifies the parts. However, humans remain in control, validating the failure mode and approving the execution window. The result is a planned fix instead of a catastrophic failure. In complex systems, like a boiler or turbine, the agent's role is to coordinate an investigation across departments. It identifies risks and drafts a cross-functional review, ensuring that no autonomous changes are made to these highly interconnected and sensitive systems without human engineering oversight. In summary, Agentic AI acts. It doesn't just answer. Authority must be risk-based, and value is only realized when the AI is connected to real-world work execution. Governance and human judgment remain our most important safeguards. Our approach is grounded in industry standards, from NIST and ISO to ISA 95. These references provide the framework for our governance and asset management principles, ensuring we align with global best practices. Regarding the content of this deck, all visuals and frameworks are original or conceptually referenced to ensure compliance and minimize copyright risk. We encourage you to use company-approved data when adapting this for internal use. As we close, remember that Agentic AI is an operating model change. It requires connecting technology, people, and controls to create enterprise value. It's a journey that must be managed with discipline. Thank you for your time. I'd like to open the floor for discussion. Based on what you've seen today, where should your organization first permit agentic AI to assist, draft, or act?